talked about a SpaceX rocket body that ended up crashing into the moon. Now we're looking at another end-of-life spacecraft story, except this one is coming back toward Earth. This story comes from an August 19th Associated Press report. Rescue mission is called off for NASA's aging Swift Space Telescope. NASA's Swift Observatory has spent more than 20 years studying some of the most energetic events in the universe, including gamma-ray bursts and exploding stars. But its orbit has been getting lower, and intense solar activity has caused it to lose altitude faster than expected. NASA paid Katalyst Space Technologies $30 million to attempt something pretty remarkable: rendezvous with Swift and boost it back into a higher orbit. That rescue mission has since been called off. Problems controlling Katalyst-linked spacecraft ultimately prevented it from attempting to capture and boost Swift. According to the Associated Press, Swift is expected to re-enter Earth's atmosphere later this year, although it is said this probably won't happen before October of 2026. So I wanted to see what was actually happening to its orbit. And instead of just showing you my results, I'm going to demonstrate where you can actually obtain the data yourself. Now, if you're new to my channel, I'm Dr. Amanda Fetch, aka Dr. Amanda Analytics. My research focuses on space situational awareness, artificial intelligence, and using orbital data to better understand what's happening in the space environment. And for this particular analysis, we're going directly to the orbital data itself. Now, the data that I'm using comes from spacetrack.org. Spacetrack does require you to create an account if you want to follow along. This is also free, by the way. So go ahead and navigate over to spacetrack.org. Once you're logged in, go to the query builder part of the site. For this particular analysis, I'm using the GP history class because I want to see how Swift's orbital parameters have changed over time. Now remember, Swift's NORAD catalog ID number is 28485, so that's our first variable. Then I'm using epoch to specify the period I want to examine. Now for this analysis, my query begins on January 1st, 2024 and runs through August 20th, 2026. Now I'm going to share this query so you can build the same thing yourself. Now once you've entered in all the parameters, select CSV as the format, hit build query, and then run it. Now that gives us the GP history that I'm bringing into Python for an analysis. And you're going to notice there can be multiple GP records on the same day. So I'm not treating every row as a separate day. I consolidate those records into daily observations using the median before analyzing the trend. And so this is the analysis, what we get. At the beginning of 2024, I calculated Swift's mean orbital altitude at approximately 522 kilometers. By August 20th, 2026, it was approximately 344 kilometers. That's a decline of about 178 kilometers. And there's a nice external check that we can do. AP reported Swift at approximately 345 kilometers when the rescue was called off. So our analysis of the spacetrack data is right in line with that reported altitude. Now the next part is where it gets really interesting. I calculated the average rate of altitude loss and normalized each year to 30 days so we could compare them. Now in 2024, Swift lost an altitude at an average equivalent rate of about 3.54 kilometers per 30 days. 2025, 5.63 kilometers, and through August 20th of this year, 2026, 8.55 kilometers per 30 days. So with that being said, Swift gets lower, we're seeing the rate of orbital decay increase. Then I calculated the actual rolling 30-day altitude loss. And during the most recent 30-day period in this data set, Swift lost approximately 9.95 kilometers of mean orbital altitude. Now don't take 9.95 kilometers and simply extrapolate forward to predict an exact re-entry date. Orbital decay really isn't that simple. Atmospheric density, solar activity, spacecraft orientation, other factors can affect how quickly an object loses altitude. But that's why I think this will be interesting to follow. So what we're going to do is we're going to turn this little experiment and we're going to keep pulling this on a month-over-month basis until pretty much Swift re-enters. Now with that being said, we can go ahead and navigate back to Swift spacetrack data. We're going to use that same NORAD catalog ID and object number, same mythology, and then we're going to start building new charts and new observations. So we're going to actually be able to watch the trajectory change as Swift gets closer to re-entry. And because I've shown you where the data comes from, you can also follow along and do your own analysis. Now, Swift has been an extraordinarily, successful mission. So this isn't a story, again, as in SpaceX, about a failed mission, or in this case, a failed telescope. For me, it's a much bigger question surrounding space sustainability. We spend enormous amounts of effort figuring out how to put spacecraft into orbit. Now, as the space environment becomes more crowded, we really also need to think seriously about what happens when we're done with them. Now, NASA actually tried to extend Swift's life, and the difficulty of doing so demonstrates just how challenging servicing and end-of-life management can be for a spacecraft already in orbit. So I have a question for you as we wrap. As we launch more spacecraft into orbit, should every mission be required to have a clearly defined end-of-life plan before it ever even leaves the ground? Let me know what you think in the comments. And we'll be back next month with another analysis. We'll also continue to do our weekly analysis and news as well. Until then, keep looking up and keep asking questions. I'm Dr. Amanda Analytics, signing off. Take care.